Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the new chapter of vector calculus. So finally we have finished our previous chapter that was basically calculus only, but that was the normal calculus, right, without any vector quantity involved. So right now we'll study about vector calculus and like we have covered calculus in brief. Trust me, no one has studied that much because what we've done, we've gone from zero to highest level. I have told that in my last lecture. So this chapter, right, vector calculus, obviously all branches have to follow except computer science. Computer science, guys, you just have to follow the single and double integration. In double integration, mostly I've covered few things, but one video I will do in this vector calculus chapter itself, I will tell you that will be prerequisite for integral vector calculus that you just study, because there I have explained double integration and volume integration, triple integration, right? So triple integration we have already done, but few more things I need to explain on that. Why am I explaining in this vector calculus chapter? Because that will help us in later stage, right, while we'll study about the vector integral. So that's why it is known as a prerequisite of vector calculus, vector integrals. So that video only you have to see. It will be two lectures. I will tell you, like I will tell you in the course curriculum also. And for other branches, right, all branches have to follow wherever it is written curl, divergence in your syllabus. Just go to a syllabus in engineering mathematics and see curl, divergence, all those things are written. Then that means vector calculus is included in your syllabus of your branch. So I think most branches like mechanical, EC, EE, IN, civil, chemical, all these branches have vector calculus except CS, and other branches you have to see your own syllabus. I have seen syllabus for these branches. So let's start. So obviously right now the first lecture will be lecture 0A. So this will be basics of vector algebra. For those who have forgotten their 11th and 12th and they haven't studied vector algebra in a while, so they can watch this lecture, else you can simply skip it. You can watch it in 2x. You can just go through the notes, because whatever I will explain here you already know. I think 90% of people already know. Okay, so you can go through the notes and just quickly revise, but this is just for revision purpose. So all this lecture 0, right, this will be lecture 0A, and there will be lecture 0B and lecture 0C. Lecture 0B and C will be for vector integrals. That also is for revision purpose about the double integration and triple integrations. Who doesn't understand about cylindrical symmetry and spherical symmetry, they can watch that lectures. Okay, but this one I hope most of you don't have to watch this, but who haven't studied 11 and 12, or you have come from diploma, you can watch this lecture. Okay, so obviously let's start. What is a vector? What is a vector? We already know, like the definition of vector is quantity with magnitude and direction. So here I have 2 points A and B. So if I'm moving from point A to B, so let's say I'm moving from Delhi to Kolkata. So I can go from Delhi to Kolkata straight through a flight, or I can take a break, right? I can go from Delhi, then come to Bangalore, and then go to Kolkata. That's like a very long distance I have to cover, right? So this is like the distance, right? Distance. This is known as the distance. Okay, and this distance has different direction, but with distance is a scalar quantity. Hence we are not concerned about the direction here. Okay, but here I'm moving in different directions, right? You can see different directions I'm moving. Now if I go from straight here to Kolkata, like from Delhi to Kolkata, so I'm taking a flight, so I'm going straight point A to point B. Flight goes point A to point B straight. Obviously it also diverts sometimes, but mostly it is straight only because it flies through air. So this, what is this known as? Like in physics you already know all this. This is known as the displacement, right? Displacement. Okay, now all this is fine. These are scalar because distance is a number, displacement is also a number, but with displacement we generally also mention a direction because I'm moving in a particular direction. So distance is just a scalar quantity because it doesn't have any direction associated with it. Scalar quantity, and this displacement is a vector quantity because it has a direction associated with it. You can like you have already studied in physics, right? So this is known as the shortest path between A and B. Okay, so yeah, this is one thing. Okay, so now, so I told you, like, vector quantities are those quantities which have like some magnitude and direction associated with it. So angle a vector quantity? because angle can be measured in clockwise and anti-clockwise direction. So it has a direction and it has also a what magnitude of it, 30 degrees, 60 degrees. So if I'm moving in this direction, that means I'm in anti-clockwise direction, and if I'm moving in this direction, that means I'm in clockwise, same direction as the clock. Now, is this a vector quantity? No, this is not a vector quantity. Now, why is this not a vector quantity? Why it isn't a vector quantity? Because along with those two things, it has to also follow the vector law of addition. So a vector quantity should always follow the vector law of addition. Now, what is vector law of addition? So let's say, like, if I have two forces in this direction, just hold on a second. Yeah, if I have one force in the x direction, like if you know already I cap, that's fine, we will study about I cap later on, but just for the sake of it, I'm explaining with one example. So in this direction, I'm applying a force of, in the x direction, right? This is x direction, I'm applying a force of 4 Newton, okay? And in the y direction, in the perpendicular direction, I'm applying a force of 3 Newton, okay? So this is in the, so I will mark the coordinate, this is like in the x and y, okay, x and y. So if I'm applying force in 4 or like in x direction 4 Newton and y direction 3 Newton, then can you tell about the resultant force? So simply I will add these two. Now whenever I'm adding these two, I have to follow the vector law of addition. Now what is the vector law of addition? Basically we make like a parallelogram and then we connect the vertices, right, from the tails to the end point, diagonal of the parallelogram. So now can you tell me what is the magnitude of this vector? This is also vector force, because overall if I'm pushing you in x direction and I am also pushing in the upward direction also, y direction, then overall you will go somewhere like this, in between those two, right? You will not exactly go up or you will not exactly go in front, you will go somewhere like this, something like this, right? Some slant. So this overall thing is 5 Newton, okay, if you do the vector addition, because yeah, this is in the I cap direction and this is in the j cap direction. Like if you don't understand this, don't worry, for the people who already know, they can take the analogy from this. Now force is a vector quantity. If you have studied physics, you know. So that is exactly basically what is happening to this block. If I apply some force to this block in this direction, in the x direction of 4 Newton and y direction in the 3 Newton, so overall the force vector can be written as this, okay? And how can I write my force vector? I can write my force vector as, now I can break this down to two components, x axis and y axis. Basically this is like a triangle, right? This is like a triangle, okay, and this is 90 degrees. So 5 cos theta, the magnitude, length of this cos theta will be length of this, and direction is already I cap, I don't know, x axis, and 5 sin theta, the direction of this is y axis, and magnitude already know that is 5, right? So basically I can write this force vector as 5 cos 37.13 I cap plus 5 sin 37.13 j cap. Now if you break this down, obviously you will get the desired force that we initially applied. What force initially applied? We applied 4 Newton in x direction and 3 Newton in y direction. Obviously don't forget the unit also, so they have to be same units, right? Whenever you're applying the vector quantity vector addition, obviously they have to be same quantities. But in mathematics, as we are not generally dealing with quantities like Newton or kg, those things, right? So we don't have to worry, they will be of same quantities. But do take care whenever you're solving some physics problem or you're solving some electromagnetic theory problem, right? They have to be same quantity. Vector addition has to have same quantities. So obviously I can observe that my magnitude of force will be 5 Newton, okay, and you can also find the angle of force. Angle of force is tan inverse what? Y upon x, right? Y upon x. Y is 3 upon 4, which is 37.13 degrees, okay? So this is the basic thing. Now there is another thing called tensor. So like as like our main audience is electrical EC, so they may understand. If you're from mechanical or other maths, you may not be able to understand this, or you have studied basic physics, right? Current, electricity, you have basically studied during your like schooling. So here, what is a tensor quantity? So tensor quantity is a quantity with magnitude and direction and it should also follow the vector law of addition. Now instead of, sorry, not vector, algebraic law of addition. Now instead of following the vector law of addition, it will follow algebraic law of addition. Why is this the case? Because like current, like how can I define current? Obviously we have to define the quantities, right? Current is also quantity. So if some current is flowing from here 3 amps and here 4 amps, so can you tell me what will be the overall current here? The overall current, you will simply say, yeah, it is simple, sir. It will be simply I3 equals simply 3 plus 4 equals to 7 amps. Okay, but like if it was vector, like you might say this is in y direction, this is in x direction, then this will be some I cap component, j cap component, okay, like that. But here we're simply adding it. So if you're simply adding it, it follows the algebraic law of addition, not vector law of addition. So like current is a tensor quantity. So this is an example of a tensor quantity. So that's the difference between vector quantity and tensor quantity. So now let's go to the vector. So basically, I hope you know the representation of a vector. So vector obviously has a magnitude and a direction. So like what is the direction? Direction is this, right? From A to B. It is going from A to B. It is known as the initial point and it is known as the terminal point. And sometimes this also is represented as head and this as tail. Okay, this is a geometrical graphical representation of a vector quantity, magnitude and direction. Okay, now let's go to the mathematical. Mathematically it is written like this. If I have vector A, it will have some magnitude and it will have some direction. Now this is known as the direction. So basically A is the magnitude of A and A cap, this is known as the cap. A cap is the direction of the A vector, or A vector is also written like this, that it is the unit vector in the direction of A. It is a unit vector in the direction of A. Okay, so basically direction and unit vector are interrelated. Direction means unit vector means direction. So we use unit vector only for representing direction mainly. So for representing direction we use unit vectors. So this is a very important point, key point. Okay, so direction means unit vector. Okay, and obviously unit vector means direction. So this is a very key point that you have to understand. Okay, so this you have to understand the relation between unit vector and direction. Just don't see the unit vector as a unit vector. It means it represents something. It is a direction because the magnitude is 1. So magnitude will always be 1, but it represents a direction. Okay, so let's understand about another vector, that is a null vector. Vector which has 0 magnitude. Now does it have any direction? Yeah, it can have any direction, right? It can have any direction, but I won't be able to represent it because it is just null, right? Point. It doesn't have any magnitude, so I can expand the arrow. I can't expand the arrow. But you might say then why it has a direction? Because we don't care. We don't care because like if you apply 0 Newton force, you apply up, down, straight, in front or back, it doesn't matter. It doesn't, right? If you're applying 0 Newton force, so it won't move the block, so it doesn't matter, right? So any direction doesn't matter. Doesn't matter. Okay, so it has any direction, right? Undefined direction, we don't know. Okay, we don't know. Now another thing is, if you are multiplying a scalar with a vector, will it change anything? So scalar means a constant number. So basically what it will do, it will just change the magnitude of the vector. So let's say, but also it can also change the direction if we are multiplying a negative number. So now if I am multiplying a negative number, so it can change the direction, but when you are multiplying it with a negative number, right? So let's say I'm multiplying minus 1 by 2. So if I'm multiplying minus 1 by 2, so my vector will be this, right? Vector will be this. So obviously the direction has been changed over here. So just take note of this, that even if I multiply a scalar, the direction can change, but only in the opposite direction. So basically I will write here, direction can change but only in opposite direction. Okay, so yeah, that is one thing. And yeah, let's see if I multiply 2a. So I multiplied minus half, so it changes the direction. If I multiply some positive number, so it will just increase this. Okay, increase the magnitude. They will be all parallel, right? They will all be parallel because the direction isn't changing exactly. It is just becoming opposite or either in the same direction. Okay, the magnitude has changed, so this will be 2a, right? Okay, so yeah, this is about multiplication with scalar. Now let's understand like unit vector. Okay, in terms of a, like graphically, let's understand vector with a unity magnitude. So for a vector to be unit vector, it has to obviously have unity magnitude. Okay, and the direction should be in the direction of a. Okay, of its vector, that is basically a. So basically what I do, I just simply divide this by its own magnitude. If I divide this vector by its own magnitude, then I will be able to get what? I'll be able to get my this vector by its own magnitude. Then simply I will be able to get the unit vector. So basically the magnitude of this is simply 1. Okay, unity, and direction is same as the a vector. So basically that's why this is known as the known as the representing the direction of a vector. Now let's go to the next slide, that is a unit vector along coordinate axis. So I have told you that I will tell you about the ijk. So if I have coordinate axis, we already know x, y, z. We have done integral problems, right? X, y, z, z. Now along the x axis, the unit vector representing this x direction is known as the I cap. So you can observe it is 3-dimensional and the magnitude of this is 1 because this is representing 1, 0, 0. So this is represented as I cap. Similarly, y direction j cap, z direction k cap. Okay, and also this follows the right hand law. So we'll write this in okay. So basically if this follows the right hand law, what will happen? What does right hand mean? So you can observe my 4 fingers, right? What do? You place your 4 fingers along the direction. Okay, and if you just, okay, this is in this side, so okay, if I move from, I've done something wrong, this shouldn't be this. Okay, I have done something wrong. This will be x and this will be y. Sorry for that. Just have to move this things. Okay, so yeah, I had done something wrong there. So basically what do? You go keep your hand along the x-axis, okay, and then move towards y-axis. You will see it's up. Basically if I'm keeping my hand towards x-axis and then moving towards y-axis, I'm observing that my thumb will be in the up direction. So obviously this will represent the next axis, that is the z-axis, right? So obviously xy coordinates also follow right hand rule. Now you can move from y to z, and if you move your thumb from y to z, you will see it coming towards me. So basically it is representing the x-axis. So basically what you do, we go in the clockwise direction. So first I will get x, then I will get y, and then I will get z. Okay, if I move in the clockwise direction and then again I'm following the same loop again. So if I'm moving in the clockwise direction, okay, I will get back the same thing. So if I'm moving from x to y, okay, curling my 4 fingers x to y, and my thumb will represent the other axis, z. Okay, if I'm moving from y to z and curling my fingers, I will again get back to x. But if you move in the anti-clockwise direction, it will simply be opposite. So if I move from z to y, I'm moving from z to y. Okay, if I move from z to y, it is towards you, right? Moving from z to y towards you. If it is towards you, that means it is this, right? That means there is a negative x-axis. So we will get the x-axis but in the negative direction. So that thing you have to follow. It follows the right hand law. So we'll do more this in the cross product topic, so there we'll understand. Now if we have been given a point, can you tell me the position vector in 2D for that point, right? So basically what we do, we find the x component and y component and simply write it down. So like whatever there is, this, let's name this is 0 comma y and this is x comma 0. So what will be my position vector, right? So basically this helps us in finding the position of this p bar, right? Position vector helps us, the name suggests itself, helps us in finding position of p. Okay, so basically what will be my position vector of p? What will be position vector of p? It will be simply like x1 x2 minus x1, right? Now as we are computing from origin, so x1 is 0, so it will be simply x minus 0 into I cap in the I direction. So we have to obviously multiply the direction. So this is representing the magnitude and the direction is this I direction, right? Then plus y minus 0 j cap. Magnitude is y and direction is in the y axis, so it is j cap. So obviously my I write it like this: OP vector equals to x I cap plus y j cap. Okay, and you can observe that this is following a somewhat like a right angle triangle. So if it is like a right angle triangle, so obviously I can compute the hypotenuse, right? Magnitude of this vector. The magnitude of this vector will simply follow the Pythagoras theorem. It will be simply x component square plus y component square whole under root. So it will be x square plus y square whole under root. Okay, and yeah, let's understand the position vector in 3D. So if you have a position vector in 3D, the same thing only. So you will compute x like okay, let me just write this. This is fine, right? Let me just compute the directions. So y, yeah, this is fine. So you can follow the right hand law here also, and you can see that all these are following convention. So if I have a point at xyz, right? If I have a point at xyz, what will be my position vector? So simply you can write your position vector p as, like, this point is origin, right? So I'm computing from origin. So you have to compute from where the tail is up until the head. So this is the tail of the vector. Let me write it down. Tail, and this is the head. Okay, so you have to take the difference of head minus tail, basically nothing else. So pretty simple concept. And plus I cap plus y minus 0 j cap plus z minus 0 k cap. So this will be x I cap. My OP vector will be x I cap plus y j cap plus z k cap. So what is the magnitude of OP vector? Magnitude of OP vector is simply x square plus y square plus z square. Okay, so yeah, this is very simple. Like again, you can use the Pythagoras theorem and you will be able to figure out right what is the magnitude of OP vector. Simply it's a cube, and z cube you can figure out. Now let's come to first question. So I wanted to compute the direction of the vectors. So yeah, if I have given 2 points, can you compute the vector AB? Now head and tail, right? What is head and what is tail, that you have to keep in mind. Can you compute the direction of AB vector and BA vector? Okay, and is there any relation between the direction of AB and BA vector? That also we'll see. So this is in 3 dimension, right? So it's in some 3-dimensional space. Some 3-dimensional space. I don't know what space it is. So this is X. Okay, I can write it like this: X, Y, and Z. Okay, so this is X, Y, and Z. So I have messed up the coordinates over here. Okay, what I can do is can write it like this also. Okay, because generally we write X here and Y there and Z there. So that is the convention, that is what I am following. So if I have, so this is 1 comma 2 comma 1. So 1 in X direction, then 2 in Y direction, and then 1 positive 1 in Z direction. So I'm somewhere around here, right? So if I'm somewhere around here, I will mark those points. This is my A point. Okay, And what about my B point? So B point is minus 1 in x direction, then 0 in y direction, and then 1 in z direction. So basically I mean up until here, right? So this will be somewhere around here. This is a B point. Okay, so basically what is, I have two vectors, right? I have two, like if you guys want to assume this thing that I have two vectors, one is here, okay, and another one is in the back side behind. But what I am interested in is these two vectors, one coming from A to B and one coming from B to A. Okay, coming from A to B and one coming from B to A. So basically what you do, you take the you take the head minus tail, that is what you do, right? I told you that is what we do. Or you can compute, like we'll do that later on. First let's compute AB, right? So if I want to compute AB, so AB vector is head minus tail. So basically head is this time B, right? B point. So minus 1 will come first, then minus 1 I direction plus 0 minus 2 J direction plus 1 minus 1 in K direction. Okay, so basically they're in the same, like there is no height associated with it, so there will be no height, truly simply in the xy plane. Although you can't visually see, but like I hope like mathematically I'm able to make you understand this. So this is minus 2 I cap minus j cap, right? So what is the direction? So direction is basically the unit vector. So unit vector AB equals to, basically the vector will be at the top, minus I plus 2j divided by the magnitude. What is the magnitude? Magnitude is 2 root 2. So to simply minus I plus j divided by root 2. Okay, so this is my direction vector. Now let's compute the opposite one. Okay, let's compute the opposite one. So if I want to compute the opposite one, basically like two things you can do. One is, I know, like, or you could have solved it like this, that my, like this is method 1. Okay, and although this doesn't require any method, but still, like this is the most basic things. So or you could have understood like this, that what is my OB? My OB vector. What is my OB vector? My OB vector is basically I'm moving in this path and then in this path, right? If I add these two vectors, I will get my OB vector. That is the resultant vector. I told you, right? If I connect the tail point and head point, then I will get the resultant vector. It follows the vector law of addition. So OB equals to OA plus AB vector. Now simply from here, I can evaluate my EB as OB minus OA. So always remember, if I have AB, B will come first, then A will come later. So this is how you remember, B coming first, then A coming later. Okay, and obviously you can do the same thing for the second question as well. What you have to find BA, right? So basically your BA vector, again you can do the head tail subtraction. So this time my head and tail have interchanged. So this time my head is this and tail is this, right? BA, this time head is this and tail is this. So this will be 1 minus 1 of minus 1 in the I direction plus 2 minus 0 in the j direction plus this will basically get 0 because 1 minus 1 in the k direction. So this will be 2 I cap plus 2 j cap. Now obviously what will be my direction vector? So my direction vector, again I have to divide by magnitude, and you can use this for the second method also, with the help of second method also. This will be simply equals to 2i plus 2j divided by 2 root 2, right? So this will be simply I plus j root 2. So basically what am I observing? They are the same thing, right? They are almost the same thing. Of magnitude will anyways be same for unit vector, but direction is just opposite. So what I can say is this is not just, this will be A cap, right? This will be cap. We always represent unit vector with cap. So A cap of AB equals to minus of A cap of BA. Similarly, I can write AB vector magnitude will be same for them. Okay, you can check for yourself, will be opposite of BA vector. Okay, just the direction will change, magnitude will be same for them. Okay, so yeah, this is the case. So like let's now go to few more cases, that is types of vector. So we have different types of vector, right? One is equal vector. So if you have equal vector, that means they have the same magnitude and direction. Okay, represent the, also they have to represent the same quantity. If I have force, they should represent the same quantity, that is Newton. So let's say I have been given force vector 3I plus 4J Newton, and but this won't be in mathematics, this won't be that much of an issue, because we won't see the units, right? We won't see the units of quantity. Okay, so also I have a velocity vector V, which is meter per second. Okay, so what do we see? Units are not same, right? Units are not same. Units are not same. So obviously if units are not same, these vectors won't be equal. But in mathematics, we don't write units, so we can take them as same only. Okay, in mathematics, because once units are written, obviously they are not the same quantity, right? So but in mathematics we won't care about units. Okay, so like there is another concept, there is another thing known as free flowing vector. So if I have free flowing vector, basically let me just do one thing. I haven't written it down, I just remembered. So a free flowing vector, right? What is it? Free flowing vectors. So basically, if you have been asked to draw a vector, so I will like formulate the question for you. Draw a vector in northeast direction. Okay, so basically northeast will be something like this. This is my south, this is my north, this is my east, and this is my west. Okay, so if we have to write a like a vector in the northeast direction, how will you draw? So you will draw it like this. I will also draw a vector in northeast direction of magnitude 5. It doesn't matter, any magnitude, right? So basically what you do, you take a vector and you draw it in the northeast direction, right? It's simple as, so this is some AB vector. Now here, what is the impressive thing is that I have drawn this vector right here. Okay, someone else might also draw the same vector from here, right? From here someone else might draw, and they will also be correct, and this guy will also be correct. Now what is the concept? Basically I can draw this vector anywhere, right? So here coordinates are not written. So if coordinates are not written, right? The start point and end point are not written. Coordinates hence these are equal vectors. They're same vectors, they represent the same direction and obviously the magnitude, and obviously they haven't given out their coordinates, right? Endpoints and start points. If they haven't, they will be considered as equal vectors. Okay, and obviously they will be considered as free flowing vectors. So these are my free flowing vectors. If coordinates are given, then that won't be my free flowing vector. So I will just do one thing. I'll copy this and then again paste this over here, and let's color this as green, and let me name this vector differently, some random EF. Okay, and here I have been given the coordinates, right? 0 comma 0 comma 0. So this isn't a free flowing vector anymore. 0 comma 0 comma 0, not a free flowing vector. Okay, that you have to take care of, because I can take it anywhere, right? I can't take it here, take it there. Okay, because it is fixed, endpoint is fixed, I can move it. Okay, so this will not a free flowing vector. Okay, this will not be a free flowing vector. That is very important. And what will be a free flowing vector, what will not be a free flowing vector. So like there are more another types of vectors, parallel vectors. So if the vectors are representing the same direction, represent the same quantities, okay, even if they are not free flowing, still they will be called as parallel vectors, not equal but parallel. Okay, but like magnitude can also be different, right? Magnitude can also be different in this case. So like let's say I have this vector AB. Okay, AB vector, I have this. Now what say if I cut this vector in the middle, right? I keep the direction as same, the magnitude has changed, and let me name this point C. So obviously these two vectors, right, overall this AB vector and this AC vector are parallel, this CB vector and this AC vector are parallel, they are parallel. Even if I move it, right, even if I move this thing, okay, but it is going towards the same direction, this is some EF, okay, then also it will be a parallel. If I cut this vector and keep it here, right? Okay, let me do one thing. If let's say I cut this vector and then I paste this vector here, okay, so obviously the direction is same, okay, and it is free flowing because I haven't mentioned the coordinates, so I can paste this anywhere, I can keep this anywhere. So this is free flowing and this will always be parallels. Okay, now what are collinear vectors? Basically from the name itself you can understand that vectors will lie in the same line. So what do I mean by this? Let's say I take this vector, right? So okay, this has copied everything, just hold on. If I take this vector, paste this over here. Now let me just write this here, I forgot to write this that time. This is parallel, okay, and this, right, if I just cut it and keep it on the same line, if it lies on the same line, okay, this line is extending, right, I just keep it at this magnitude. If I extend this line and if another vector lies in the same line, obviously it will be collinear. So this and this will be collinear, right? This will be collinear because they are lying in the same line. Okay, but this vector, if I now keep this here, okay, and obviously the coordinates have to be marked, right? The coordinates have to be marked. So let's say this is some xy comma z, okay, some x1 y1 z1, okay, and this is some x2 y2 and z2. Then obviously I can say that these are not DE. These two vectors are not coordinated because their endpoints are not same, right? Their endpoints are not same. They have to lie in the same line. Even though their endpoints are not same, that is fine. Endpoints is not same, but obviously they are also not lying in the same line, right? This is a different line, so not collinear. Not collinear. Change the color. Okay, so these things you have to care. Obviously these two are collinear, right? Now coplanar means they are lying in the same plane. So if I have this, right, something like this, if all the vectors are lying in this xy plane, then those vectors will be called as coplanar. If all the vectors lying in the this plane, right, yz, then those vectors will be called as coplanar. co-planar. So basically, when you're talking about collinear, right, we generally tend to talk about two vectors. Why is this the case? Two vectors. And when we are talking about coplanar, right, we generally used to talk about three vectors. Basically, with two vectors, right, you will be able to form another plane. Okay, so you can form another plane. So at max you can have 3 dimensions. So obviously there is a discussion about three vectors, whether these three are co-planar or not. So we don't discuss about two vectors because like another frame another plane can be formed, right, with two vectors. Like just the example here, this j and I vector, I can also get another plane, right, another vector that is perpendicular to these two. So it hasn't any meaning because I and j anyways will lie in the same plane. So just to create any meaning, we generally discuss about three vectors in coplanar vectors, because if I have k, j and I, these three vectors, are these three vectors coplanar? No, because all of these two are lying in the same xy plane, but it is lying in some other plane. That's why. So we generally try to discuss about three vectors in coplanar, and for collinear we generally try to discuss for two vectors only. Why? Because anyways they are lying in the same plane. I'm more concerned about the line. Are they in the same line? Okay, so yeah, this is the case. Now, like very important, if vectors are free flowing, okay, then your parallel vectors will be also known as collinear vectors. Okay, because they haven't mentioned any endpoints, right, any endpoints. So that is very important. Okay, so yeah, let's go to the most important topic, that is the dot product. So from here obviously your flavor of vector calculus will start, because dot product will be used multiple times. So this is also known as the scalar product. If I can write here, scalar product. Okay, now what is the definition? Basically a and b are two vectors which are non-zero and angle between them is theta. Then the scalar product or the dot product, which is written as a dot b. Now just don't confuse this with simple product what you have learned like in class 5-6, like 5 times 3. This is different, right? This is dot product, because there will also be another product known as the cross product, and those two things are different. So a dot b is defined as this: a dot b equals to mod of a mod of b cos theta. Okay, so like you know already this, I hope. And it is known as scalar product because it has no direction, right? Simply a constant number, no direction. Simply a number, just has magnitude, no direction. Okay, so another important point about the theta. So I have two vectors and the angle between them is theta. So how do we define the theta? So angle between the vectors should always be defined like this. Let me write this thing. Angle between vectors obviously you can say they are connected from tail to tail. So always when you are computing the angle between these two vectors, any two vectors, you will always find the angle between the tails of them, right? Connect them between tail to tail and then you compute the angle. Okay, and one thing you will observe, your angle theta AB will be in the range from 0 degrees to 180 degrees. Why is this the case? Okay, why is this the case? Because what we're doing, we always compute the acute angle, right, which is not the acute, I forget the ranges, but we will always compute this angle which will be 0 to 180. So there can be two angles, right, between A and B. I'll just show you one example. Let's see this example, right? So if I have a vector B here, okay, and a vector A here, this is the first thing, and I have told you that this angle, right, this angle is 15 degrees. Now can you compute the angle between A and B? What will be theta AB? So I can compute it like this. Either I can go from here to here, right? Or I can go from here to here also, right? There are two angles involved. So this angle, what is this angle? This is 180. So 180, this is angle. This angle is simply straight line, right? 180. 180 plus 15 is 195. 195. And another angle theta AB is simply this, right? So this is also 180, and if I subtract 15, I will get 165. Now obviously which one to choose? So we'll choose the angle which is less than 180. Okay, so basically this is our convention basically. So we choose angle between 0 to 180. So we'll choose this angle, right? Not this angle. Okay, so our answer will be 165. Another thing is that the parallel shifting of vectors does not change angle. So if I shift both of these vectors, right, parallelly, okay, if I shift this here along this line, if I shift this in the top, if I shift it on the right hand side, parallel shifting of vectors won't change the angle between them. Okay, so this is also very important point. Parallel shifting. Okay, I don't have space much. Can put this at the top. Parallel shifting of vectors won't change theta AB basically. Okay, so yeah, this is about the angle. So let's do one question from basic question and we'll understand. So here you have been given these two vectors, right, and you have been given the angle between the heads. Now can you tell me angle between the tail? So what you'll do, you'll do the parallel shifting. So first what you'll do, you want to connect the tails, right? So your first criteria, at least let me connect this tail to this head. So I will move this more forward. So if I move this forward, so basically I'm just shifting it parallelly. I'm doing nothing else, and this head is still here. Okay, but obviously I've just moved the parallel shifting, right? I should write here not theta AB, just simply angles, because it won't change any angles, right? Not only theta AB, any angles. So yeah, I move this, so this angle will still be what, 60 degrees. Now if I move this along a straight line here, right, obviously what will happen, I want to connect the tails, so I will move this along this. So this is again, okay, let me just color this anyways the same color, because else you get confused. So now what I will just copy this and I will move this forward here. So if I move this forward, what will happen? Just hold on. Yeah, this angle is still 60, right? If this angle is 60, what is this? These two angles will be same, right? These two angles will be same. Okay, this is a simple two straight lines crossing each other, so the angles here and angle here will be same. That basic thing you know. So this also will be what, 60 degrees. 60 degrees. Okay, let me check everything is recording or not. Yeah, this is recording. This is also recording. Fine, great. Yeah, this is also recording. So this is 60 degrees. So like I hope you got the point that answer to this question will be 60 degrees. So this is how you compute the angles between two vectors, simply by shifting parallelly. So now let's understand the next concept, that is the most important concept, basically the dot product. So we have understood the theoretical part of dot product. Basically dot product is A dot B equals to magnitude of A into magnitude of B into cos theta. Now from where does it came? So what scientists did was, like I've learned this from where I've studied. So they told, like they are telling that what we try to do, we try to represent physical quantities. So when we try to represent physical quantities, so there are some methodologies. So we have defined dot product like that. So let's say I am pushing this block in this direction, right? This direction. Let me just copy the block here. I had a block, right? Where did that block go? That's way, yeah, here. This also I copy. I will just do show this differently. Yeah. So now let's say I am applying a force to this block. Okay. We just push this block more forward. Yeah, here. Applying a force to these blocks in this direction. Okay. In this direction. Now I want to know. Let me erase this only. I want to know in x direction how much actually force is getting. How much this block is how much force this block is experiencing in the x direction. So I want to know in the x direction. Okay. So x direction is the vector I, right? So basically, if I project this, right, if I project this in the x direction, there will be some component which will act in the x direction and some component in the y direction. I don't care about the y direction. I only care about the x direction. That will only move the block forward. In the y direction, if there is no friction, that will not do anything, right, to my block. Okay, that will not do anything to my block. So if I'm only like concerned with the x direction, so I can write it like this, that the projection of b, this is the b vector and this is the a vector, b vector and a vector on a, projection of b on a will be represented like this, a dot b into mod of a. Or how can I break this down component? How can I break down this component? This component you can break down like this. So basically projection of b on a will be a dot b into mod of a, or you can write magnitude of b vector cos theta. B cos theta is the angle between them and cos of this angle. So this you have been studying since childhood. So that is what we do. Magnitude of b cos theta. Now how else can I write it? So basically now we are concerned with b cos theta, right? How to compute b cos theta? So we defined it like this, that a dot b will always be equals to magnitude of a into magnitude of b into cos theta. Now from here I can compute my b cos theta, right? I can take this down in this side and this will be my b cos theta, basically the projection of b on a. So b cos theta will be equals to simply a dot b divided by magnitude of a. Okay. Now this is a simple formula. This you have to obviously don't have to remember, because you can just remember the a dot b. Now another important point is this can also be written like this, right? Basically this can also be written like b vector in the dot with direction of a vector, right? Dot with direction of a vector. So you can also write it like this. Okay. So yeah, this is all the basic things only. I hope you know all this. So just computing the projection, if you just put a sunlight over here, okay, we have studied projections, right? If you just put a sun over here, you will see that whatever shadow this is giving, it will be projected on this here, right? And what is that shadow? What is the magnitude of the shadow? Direction I will know, it has to be in the direction of a. That's why direction is a cap, and magnitude will be this dot, right? Not simple b. Magnitude will be b, magnitude of b cos theta, right? That is very important. So this is telling me that magnitude, and along the direction is this, right? So this is the magnitude, right? This is just a magnitude, not the direction. Here there is no direction, so direction is along a direction. So this is just a magnitude, very important. The component of b on a, magnitude. Okay. So yeah, so this is basically the concept behind dot product. So like if I do dot product, there are a few properties. So obviously scalar product is commutative. So basically if I do a dot b let me change the color. Okay, no, this is bad. And if I do b dot a, they will be the same thing. Okay, it won't matter if I do a dot b or b dot a. Now if I multiply any scalar, right, this will be scalar simply, not this. If I multiply any scalar, we can do this, right? These are basic things. Now obviously scalar product is distributive. So okay, no, I have done the spelling as wrong thing, so this I have to change. Scalar product is distributive with respect to vector addition. So if I have to do a dot b plus c, I can compute a dot b separately and I can compute a dot c separately, then add them up. Obviously here order will not matter, right? You first do a dot b or b dot a, it doesn't matter. You do a dot c or c dot a, doesn't matter. If you add first, you first compute a dot c plus a dot b, it won't matter, right? Order does not matter. So product of vector with itself. Now if I have to do dot product with the vector itself, what is it? It is simply magnitude of whole square. Why is it? Because the angle is 0 between them, right? Theta is 0 between them, and if the angle is 0, definitely what is cos 0? Cos 0 is simply 1, right? Cos 0 is simply 1. Okay, so then obviously it will be simply the magnitude of square, because what is a dot b? It is magnitude of a into magnitude of b. So magnitude of a into magnitude of a into 1 is magnitude of a square. Now generally when something square term like this is written, right? When something square term like this is written, vector squared, that then wherever this is written, right, that means this has come from dot product. Vector squared, then this has come from the dot product of that vector, right? Dot product of itself. So wherever there is square, like not magnitude square, or magnitude square is also fine, or simple vector square, right? So that means it has come from, where is the primitive? Primitive is dot product. So it has, we have done the dot product of the vector with itself. Okay, square means dot product of the vector with itself. Now the magnitude of the resultant vector. So like with the help of dot product we can compute the magnitude of the resultant vector also. How? So basically, how do you compute the magnitude of the resultant vector? So you have two vectors, right? One is a and b. So you compute the resultant vector. A plus b is the resultant vector, and you have to compute the magnitude. So let me just draw these vectors, a and b, and magnitude will be like we'll follow the parallelogram law of addition. I am going to compute the magnitude. So basically it will be something like this. This will be my r vector, and I want to compute my magnitude, right? So this is my r vector. So if I want to compute the magnitude, how can you write this? We can write this using this property, right? I want to compute the magnitude. So what I can do, I can write this under root of magnitude whole square. This I can write that. This computation I can do. So if this computation I am able to do, because this is representing the same thing only, then I can write basically. Now what is magnitude square? Magnitude square is basically the dot product of the vector with itself. So it will be a dot b, a plus b into dot, not into, dot a plus b. Okay, so this will be mod of a square. Now I can do them one by one. This will be mod of a square. Just hold on a second. Mod of a square plus mod of b square, and obviously if I am doing a dot b or b dot a, b dot a, it doesn't matter, right? They are commutative. So this will be, I can write it in terms of one, a dot b, and a dot b is what? Mod of a dot b is a into b, mod of a into mod of b into cos theta, the angle between them, right? So this is how you can compute the resultant magnitude of the resultant vector. There is also another vector, right? What is the other vector? So this is, let's say this is r1. Okay, and what is the other vector? R2 is this, right? So we have other vector also, this one, not like this. This will be a straight line. So this, right, this is basically r1, and this is basically r2. Now what is r2? R2, what you can write is, if I'm moving from b plus r2, I'm getting to a. Oh, okay, let me change the direction because that will be better. So what I will do, I will just change the direction It doesn't matter because anyways we're computing the magnitude, but so what is R2? You can compute it. If I'm moving from A plus R2 equals to B vector, right? Equals to B vector. So R2 will be equals to, wait a second, did I do this correctly? A plus R2 equals to B vector. No, I did this wrong. Okay, the previous one was correct only. So I want to write A minus B basically. So yeah, this will be correct only. So let me write this down. R2 vector, magnitude of R2 vector will be simply equals to magnitude of A minus B, this, and this will be simply the same formula, just with the difference. It will be minus 2ab this time instead of plus 2ab, okay, because it will come with negative sign. So these things are important, you have to remember this, okay. I know you already remember this because these are very simple things. So yeah, let me just put this more at the top so that I can get a bit of space. Yeah, so these two things you have to remember, simple things only. Now, dot product of two vectors is maximum if and only if the angle between them is 0. So obviously cos will be maximum when, obviously I can control the magnitudes. Cos theta will be maximum when theta is equal to 0. So they have the same unit vector or the same direction. So obviously the unit vectors must be same, basically the same vectors only with different magnitudes. Dot product of two vectors is 0 if and only if the angle between them is 90 degree, that is both are perpendicular to each other. So obviously both are perpendicular to each other, then angle between them will be 90, okay, and cos 90 is 0, so obviously dot product will also be 0. So projection will be also 0. There will be no projection, right? So if this force vector is in this direction, how can it project? If I even place a sun, can it project in this x direction? No, it can't, right? There is no shadow of it. It is directly upward, so it is 0. So few things you have to like click on your mind very quickly, that if two vectors A and B are parallel to each other, that means my theta AB will be 0. The angle between the vectors will be 0, and obviously I can directly compute my A dot B as magnitude of A into magnitude of B. And if I have vectors which are perpendicular to each other, right, perpendicular to each other, then obviously theta AB will be what? Theta AB will be 90 degrees, and my A dot B, what will be my value of A dot B? Value of A dot B will be simply 0, And one more point, if the two vectors are in opposite direction, so if I have two vectors which are in exactly, one is in this direction, another one is in this direction, exactly opposite direction, then what will my angle be between the two vectors? It will be in the same line but in opposite direction, that means 180 degrees. So I have 180 degrees over here, that means A dot B will be equals to minus of magnitude of A into magnitude of B, basically because cos 180 is minus 1, okay, cos 180 is minus 1. So this is basically the dot product. Now let's understand the dot product of like the vectors that we know, right? Basically I dot I, j dot j, k dot k. So I dot I equals to j dot j equals to k dot k equals to 1. Basically it is, these are unit vectors, and the multiplication of two unit vectors, same unit vectors will be because magnitude of 1 is magnitude of I into magnitude of I, which is basically 1. Now I dot j, j dot k will be 0 because these are perpendicular vectors, okay, these are perpendicular vectors. Now scalar product of two vectors in terms of components. So if I have two vectors, right, in I, j, k, and what will be the scalar product? Now you don't have to directly compute for each of them, right, every time. You can remember this, you just multiply the I components with I components, you just multiply the j components with j components, and you just multiply the constant with k components with k components. So basically your A dot B will be very simple, right? Multiply the I components A1 A2, then add the k components B1 B2, multiplication of the j components, and then add the multiplication of the k components C1 C2, okay. This is how you compute. This is how you compute. Okay, so yeah, dot product of vectors. Now there is also another formula for angle between the two vectors. So this formula you will use when you have to find the angle between the two vectors. So you haven't given the two vectors and you have to find the angle between them. So what we know the cos theta, right? Cos theta will be simply what? A dot b was equals to mod of a mod of b cos theta. So if I bring down the mod of a mod of b, it will be simply a dot b will be equals to mod of a into mod of b cos theta, and this is enough for you to remember, right? This you remember and that's it. So basically this I can what simplify, but this you don't remember. This is some mess, right? A1 A2 then B1 B2 plus C1 C2. This is a mess and you don't have to remember this. This is a mess and you don't have to remember this. And obviously what is the magnitude of each of them, right? This will be A1 square plus B1 square plus C1 square, and this will be A2 square plus B2 square plus C2 square. Okay, so yeah, you don't have to remember, just remember this is the most important part, right? If you have to find the angle between these two vectors, you just remember this. Okay, so let's do that, right? If addition of two unit vectors is also a unit vector, then find the angle between the two vectors. So they are talking about addition of two vectors. So let's take any arbitrary vector a plus b, okay, and c vector. Now they are talking, I'm getting c vector, and they're talking about that they are also unit vectors. So if they are unit vectors, that means the magnitude of this, like magnitude of a, like a is also a unit vector, addition of two unit vectors, b is also a unit vector, and the resultant, that is the c vector, that magnitude will also be 1. And they're talking about angle, right? Whenever they're talking about angle, that means you have to take care that they're talking about something with something related to dot product or cross product, that we'll learn later. Dot product, right? So obviously you have to utilize the dot product formula. So basically what you can do, you can take the magnitude on both sides. If you take the magnitude on both sides, okay, you know that this will be equals to 1. Now we can use the resultant formula that we learned, or you can derive it also. So it will be mod of a square plus mod of b square plus 2 mod of a, just hold on, mod of a, this is 1 only, mod of b into cos theta, because they have mentioned about the angle itself, right? Cos theta, and this is equals to simply, like under root of this is simply equals to 1, so I can take the whole square, okay, which is 1 also. So this will be 1 plus 1 plus 2 into 1 times 1 into cos theta, okay, which is equals to 1. Now what do you observe? My cos theta is negative half, which means theta will be what? Theta will be 120 degrees. It can be 60 also, right? It can be 60 also, but as it is negative, it has to be obviously 120 degrees, right? So basically answer to this question will be 120 degrees. Now how are they placed? Can you observe it visually? So they are talking that I have a two unit vectors. First is a and second is b, and b, angle between a and b is 120, somewhere like this. Okay, this is also unit vector, so I have to increase the width of this. The magnitude of them, both of them are same, that is 1. Now the angle between them is 120, and now if we check, if we add these two up, right, that will also yield me unit vector. If some angle is here which is less than 90, if I add those two things, the magnitude will be greater than both a and b. But here what is happening? It is subtracting the x component. So obviously by adding these two vectors, right, the resultant vectors, what we are observing is it will be equal to 1. Obviously exactly 1, it will be equal to 1. Okay, so yeah, basically I hope you are able to understand. So obviously, does the answer make sense or not? Yeah, or sometimes you also want to check, right? Yeah, it does make sense because it is reducing the magnitude also. So it is 1 only, magnitude is 1 only. So let's go to the next thing is that dot product of vectors. Yeah, I've told you, right? Projection of B on A, that I've already told you. So is that we have done already, or have I just repeated this thing? Yeah, I've already told something about the projection of V on A. Yeah, we've done about geometrical understanding. I haven't mentioned you this thing, that you can also write it like this, right? Simply write it like this, that you will write, you do B dot A, right? So if you want to do B dot A, what you can write, A dot B divided by magnitude of A, so through the vector on which you are finding the projection, so that you have to divide by magnitude. Then you just do one thing, that you divide the A vector with its magnitude again, okay, and you will get your you will get your projection vector, right? Projection vector of B on A. So this time I'm talking about vector, that time I was talking about magnitude, I told you, right? And this is the exact value of the vector. So this is, what is this? This is the magnitude or component of B on A vector, and this is what, this is basically unit vector in A direction. Right? So yeah, this is very important to understand. Okay, now let's say if I want to know this projection, right, in the perpendicular direction, can you compute this projection? Now this projection is now B1 vector, let's name this as B2 vector. I want to compute B2. So basically what you do, your B2, for computing, you first compute this projection, right, B1. Then what you do the basic thing, that is, you already know the B vector, right? You already know the B vector. So I know B1, then I will work B1 plus B2 will be B vector. So you directly write B2 equals to B minus B1. So B minus B1, right? You simply compute that. So you can compute also the projection in the perpendicular direction. Okay, projection perpendicular to A. Projection perpendicular, I can write it in text also, perpendicular to A. Okay, so this is how you can compute, right, when they are talking about the position that is perpendicular to A. So let's come to the next topic. The next topic is cross product of vectors. So here it's a similar thing only, but this time if I do cross product of vectors, right, I will also get a vector quantity. You can observe here, right, this is a direction, so I have a direction involved right now. So if I am simply doing the cross product, so I will also get a vector, right? I will also get a vector. Cross product of two vectors will be a vector. Basically what will be, it follows the right hand law, like that. So what will be the direction of the vector? Direction of the vector will be in perpendicular to both vectors A and B, of which I am doing cross product of. So direction, now this, right, this is the magnitude of cross product, magnitude basically A cross B, right, and this component is the direction, okay, which is A n cap. Okay, this component is the direction and this component is the magnitude. Okay, and this, right, this means this should be mutually perpendicular to both A and B. Okay, Now how can you compute the direction with just simply your hands? What do? You just start with A and move from A to B like this, and you will see that I have this direction A in cap of A cross B. So obviously this is the like vector, and you have to divide the magnitude with it, and you will get the normal vector, right? You can use the right hand thumb rule. Okay, so let's go to the next thing. So these are basic things now obviously the direction of AB. First what you do, you take the 4 fingers from A. Okay, from A to take the 4 fingers and then curl towards B, right? Curl towards B. Then the direction of the right hand thumb will be the direction of A in cap. These are the basic things, right? Yeah, so what is the direction of A cross B? So A cross B, if I'm applying A cross B, so you on your screen, what you're seeing, you're taking the 4 fingers and then you're doing A cross B. Okay, if you do the A cross B from the screen, that means it is coming outside, right? A cross B, if I do from the screen, if I do A cross B, that means it is coming towards me, outside, right? Towards me. So the sign is simply like this. If I draw this, yeah, sign will be simply like this. Okay, and it will come outside. Okay, towards my screen. If it is coming towards me, okay, towards me, if it's coming, then what I am observing, it is coming towards me, right? If it is coming towards me, coming outside, okay, a bow is coming towards me, then I can see only a dot, right? I can see only a dot, right? If a bow is coming towards me, what I can observe, this pen is coming towards me, I can only see a dot. If you see, you can only see a dot, right? You can only see a dot if it is coming towards you, so it will be dot. So that this sign came from this bow concept only, that if I throw a bow and if a bow is coming towards me, then obviously I will see only a dot, right? You are only observing a dot. Now about this, now if I do B cross A, if I am doing B cross A, then what will happen? I am doing something this, okay, I'm putting my 4 fingers here and then I'm curling it towards it, and the right hand thumb is going inside the skin. Now if it is going inside the skin, that means what? You're throwing, that means you are throwing, so you are doing something like this. Then what are you observing? You're just observing this portion, right? And in a bow there is like a cross thing, right? So what you will see is that it is going into the screen. If it is going into the screen, your sign will be something like this. There will be a cross sign. Okay, and this represents into the screen, that is inside. Okay, so you are throwing the bow. This time you are throwing the bow. That bow is not coming to you. Throwing the bow. Okay, so yeah, this is the concept about inside and outside thing, direction. So like this is very important concept that you have to learn. So let's go to the next slide. Now what does cross product represent in terms of geometrical understanding? So cross product basically represents the area, right? Obviously if I take the magnitude, if A and B are two sides of a parallelogram, if I take the magnitude of that, magnitude of A cross B, then I will be able to get the area, right? So area will be simply area of parallelogram can be written in two ways. It can be written in two ways. One is this: if I compute the position of vector OB cross OA, the sides of these two, right? Sides of these two, and I take the magnitude. Or what you can do, you can take also the diagonals, right? You can also take the diagonals. So homework for you is prove that it will be equals to half OC cross AB. I'm taking the magnitude, so direction doesn't matter if I take AB or OC, right? So this is the sides, and this is the diagonal. Okay, so like you try to prove basically what you'll do. You will just take a perpendicular from this, and area is simply height, perpendicular height, basically altitude into base, right? So you try to prove it. That's the homework for you. Altitude into base. Okay, so like also it also represents the area of a triangle. Okay, simply what you do, again you will compute this, right? You can drop down the this height h. Okay, so basically you can compute this. The area of the triangle will be half mod of a cross b. Okay, you can simply compute. So let's understand few properties of cross product. So this is important. Vector product is not commutative. So basically it won't be simply, if I do a cross b, and it won't be simply equals to b cross a. Okay, these are not equal. But exactly what is the relation? The relation is something like this, that a cross b will be equals to minus of b cross a, and which makes sense because it is in the opposite direction, right? Once I'm curling this, it is coming towards like outside from the screen, and if I'm coming like curling like this, it is coming inside the screen. So inside and outside, basically a straight line only, but just in different directions. So there will be a negative sign involved. Now the scalar thing is again same. So if I just simply like multiply a scalar, I can compute the vector products first, then multiply the scalar later on. And vector product is distributive with respect to vector addition, but you just have to take care of the orders. Okay, it will be a cross b and not b cross a. It will be a cross c and not c cross a. So you have to take care of the orders. Take care of. Okay, just hold on a second. Orders. Now product of a vector with itself. If I take the product of vector with itself, I will get back a null vector. We have studied what is null vector, and obviously it will have a direction, right? Any undefined direction, because the vector product always yields a vector quantity. So I will get a direction, but it will be null vector because sine angle between them is 0 and sine 0 is 0. So obviously I will get a null vector. First important point. Okay, so basically how can you say this like in words, English words, that cross product is 0 of two vectors? If the two vectors are parallel, right? So cross product of parallel vectors will always be 0. Cross product of parallel vectors will always be 0. Okay, now like there are a few notes regarding cross product. So if I am like doing the cross product with same vectors, they will be it will be null vector. And if I am doing the I cross j, again that clockwise anti-clockwise string, right? So if I am doing x cross y, I will get z, right? So you can either follow that, or you can just remember this, that if I do I, then j, and then come back to k. Okay, and if I'm moving in the clockwise direction, then always I will get, if I do I cross j, I will get k. If I do k cross I will get j. If I do j cross k, I will get I, like that. But whenever you are moving in the opposite direction, so clockwise will be simply positive, anti-clockwise will be simply negative. Anti-clockwise will be negative, clockwise will be positive, right? So this is the first thing. So like I, j, k are like this, right? If you remember correctly, this was I, this was j. Handwriting has gone by. Just hold on a second. Oh no, where am I? Here. I, j, k. Okay, so yeah, like this you can remember the basically the right hand rule and all this stuff. Now vector product of two vectors in terms of component, so it will be very difficult for you to do the vector product individually. There will come this I cross j component, this j cross I, because I cross I will be 0, j cross j will be 0, k cross k will be 0, but other components will come. But we have understood, we have formulated our simple result that your A cross B, right? If I write it like this, will be in the matrix fraction. If I find the determinant of this matrix, then I will be able to yield my A cross B. Okay, and if it is B cross A, obviously B will come here first, then A will come. So you can replace, right? And there will be negative sign if you interchange the rows. If you remember determinant properties, so obviously this is also holding true. If I'm doing B cross A, this will be negative of this. If I'm doing A cross B, this will be simply positive, right? So yeah, this is the thing. Now like another angle formula of cross product. So only use this when they have given cross product result, right? When they have given A cross B or something like that. Don't use this because we know the easier formula, that is A dot B, and it is also easier to compute A dot B instead of A cross B. So only use this when cross product is given. Only use this when cross product is given. Okay, only use this when cross product is given, else don't use it. And like what is the important factor? Unit vector that is perpendicular to the plane of A and B. So if you have to find a unit vector that is perpendicular to both A and B, you will take the help of cross product, because cross product gives a direction that is both perpendicular to A and B. So we are interested in the A in cap. So if I do simply A cross B, then divide by magnitude, I will get my unit vector, right? I will get my A in cap. But just remember, I can get both directions, right? If I do A cross B, it will be in the positive direction. If I do A cross B, it will be in negative direction. Direction will be almost the same, but one is in the positive, one is in the negative. So that's why the plus minus sign comes off here. Okay, so you can do it like this, right? You can compute, you can understand with the example of this thing, right? IJK, this one. If I'm doing I cross j, what I'm getting k cap, right? Positive k cap. If I do j cross I, I'm getting negative k cap. If I'm doing j cross k, I'm getting I cap, right? A vector, unit vector that is both perpendicular to j and k, not lying in the same plane, perpendicular, mutually perpendicular, and it is also unit vector. So yeah, that you can understand, right, from this example. Okay, so basically yeah, that's it for this lecture. We just studied the basics of vector algebra, and these are very basic things, and I know most of you guys know. Just go through the notes and you will be able to understand. And the next lecture is important. I will expect like few more of you attend that, because that is related to double integration and triple integration, and many of you may not have studied that. So that lecture is important. That lecture you can watch. So yeah, thank you for watching, and I will see you in the next lecture.